Hypergeometric distribution is a type of probability distribution used when you're dealing with scenarios where you're selecting a certain number of items from a larger group but without replacement. Unlike the binomial distribution, where each trial is independent and the probability stays the same, in hypergeometric distribution, the probability changes after each selection because the items are not replaced. So, what are the key things to remember when identifying a hypergeometric distribution problem? First, look for situations where the selections are made from a finite population and without replacement. Keywords like without replacement or drawn without replacement often signal that you're dealing with a hypergeometric distribution. Now, let's talk about the formula used to calculate probabilities in hypergeometric distribution. It may look a bit complex, but I'll break it down for you. The uppercase K is the total number of successes in the population, while the lowercase k is the number of successes you want in your sample. The uppercase N is the total population size, while the lowercase n is the number of draws or trials. I like to remember this formula with a simple phrase, yes, not all. Here's what that means. Yes refers to the first combination in the numerator, which counts the ways you can select the specific items or outcomes you're interested in. This is what you want or desire from the population. Not is the second combination in the numerator. It represents the ways to select the remaining items that don't meet your desired criteria, essentially, the rest of the population. And finally, the all is in the denominator. It's the total combination, representing all the ways to choose the specified number of items without any consideration for the specific criteria. By thinking of it as yes, not all, you can easily remember that the formula is all about first identifying what you want, then considering what you don't want, and finally, dividing by the total possibilities. All right, I think it would be better to solve some problems to really understand the formula. Let's start with a classic example involving a deck of cards. If 5 cards are drawn without replacement, what is the probability that exactly 2 of them are hearts? Since this problem involves drawing without replacement and we're interested in a specific number of successes, 2 hearts, it's a perfect fit for the hypergeometric distribution. Let's break this down. Here, uppercase K, the number of hearts in the deck is 13. The number of successes we're looking for, lowercase k, is 2. The total number of cards in the deck, uppercase N, is 52. And lowercase n, the number of cards drawn, is 5. Substituting these numbers in the formula will give us the probability of drawing exactly 2 hearts out of 5 cards, which is approximately 0.274 or 27.4%. If we relate this to the phrase I gave you, it goes something like this. Since we're interested in hearts, so the yes group should consist of the 13 hearts in the deck and the 2 cards we want. Therefore, the not group is the remaining 39 cards that aren't hearts, and the remaining 3 of the 5 cards drawn. And lastly, the all group represents the total number of ways to choose 5 cards from the entire deck of 52 cards. Looks easy, right? Now let's move on to the second example. An urn contains 10 red balls and 20 blue balls. If 6 balls are drawn without replacement, what is the probability that exactly 3 of them are red? Here, we have 10 red balls out of a total of 30 balls. We're drawing 6 balls, and we want exactly 3 of them to be red. Again, since the balls are drawn without replacement and we're looking for a specific number of red balls, this situation is also best handled using the hypergeometric distribution. In this case, uppercase K, the number of red balls, is 10. The number of successes we're interested in, lowercase k, is 3. The total number of balls, uppercase N, is 30, and lowercase n, the number of balls drawn, is 6. After calculating, the probability of drawing exactly 3 red balls out of 6 is approximately 0.23 or 23%. Finally, let's consider a lottery problem. Suppose there are 100 tickets and 10 of them are winning tickets. If 15 tickets are drawn without replacement, what's the probability that exactly 3 of them are winning tickets? Here's the easier breakdown. The yes group is the 10 winning tickets, the not group is the 90 losing tickets, and the all group is the 100 tickets in total. For the solution, we need to calculate the combination of choosing 3 winning tickets out of 10. Then, the combination of choosing the remaining 12 tickets from the 90 losing tickets, Finally, divide by the combination of choosing any 15 tickets out of the 100. This will give us the probability of drawing exactly 3 winning tickets out of 15, which is 0.1297 or 12.97%. Pretty low, isn't it? I hope these examples gave you a clearer understanding of the hypergeometric distribution and how to apply it to different scenarios. From drawing cards to selecting lottery tickets, we've seen how this distribution helps us calculate the probability of specific outcomes without replacement. If you enjoyed this deep dive into probability, be sure to check out the other videos in our probability series. Thanks for watching, and good luck on your exam.